Okay, let's take a look now at section 3.6 of your book on vector kinematics. Recall that kinematics is simply the mathematical description of motion. There's no physics as of yet. In chapter 2, we studied 1D kinematics and learned how to relate, at least mathematically, such things as displacement, velocity, acceleration, and time as objects move along a line. We now consider how we might extend this knowledge to analyze motion that is in 2D, or with a simple extension, motion that's in 3D. Now this section gets a bit more mathematical. It is included in the AP textbook as a precursor to studying projectile motion. Truth be told, in my opinion, this section is not absolutely required in order to understand and apply equations of motion for projectiles. But if more complicated motions are wished to be analyzed, this very mathematical section of your book can help provide a good foundation. Let's go ahead and begin. Recall that a displacement is a change in position. That will certainly take direction into account, but if the motion is restricted to 1D, that change in position can be easily determined by basic arithmetic as long as you ensure appropriate signs, either positive or negative, are used to describe motion that's either to the right or to the left, or up or down. Now if the motion is both right or left and up or down at the same time, displacement gets a bit harder to quantify. Recall that change in anything requires a subtraction. So delta R here is actually a subtraction of R2 and R1. R2 and R1 are both vector quantities. They represent where I am in relation to the origin, and I can write those in unit vector notation, or I could write those as a magnitude and a direction relative to that origin. Here, I want to show you how we might be able to determine delta R graphically. And the reason for that, before I do this mathematically, graphical addition of vectors or subtraction of vectors provides a lot of insight into the actual physics that's going on. I don't want to gloss over it and simply get into the mathematics. Pictures really help provide a glimpse of the cause of many things, not just how to get a result, but why things happen the way that they do. So let's go ahead and take a look at this graphically. If I were to take the difference between R2 and R1, vector subtraction means R2 minus R1 could be thought of as R2 plus the negative of R1. Where again, the negative of R1 is just the exact same displacement, but in the opposite direction. So if I want to add two vectors, here's R2, let's go ahead and draw that here. And then I'm going to add to that the negative of R1. I see that R1 points up and to the right. If I were to make that be negative R1 and add it, I would place that tail to tip on R2 and then add them. And when I add them, I get delta R. That delta R that you see here is that vector, and it's done through vector subtraction. That will become pretty important as we start to consider changes in motion, or changes in velocity, if you will, and start looking at acceleration. So this is how we might get that using vector subtraction. We could certainly measure its magnitude, we could measure its angle if we did this to scale. I'd like to do this mathematically, so let's go ahead and do this using unit vector notation. Let's just imagine that R2 was some vector that had unit vectors of, let's say that this is maybe 5i plus, looks like maybe, almost looks like 5j. So it has two components, 5 in the I direction and 5 in the j direction. Now R1, that looks like it might have components of maybe I and maybe 6j. If I want to do this mathematically, I could just simply take R2 minus R1 and write it like this. So R2 minus I1 is 5i hat plus 5j hat minus, and then just like I do in my algebra classes, I'm going to put a negative out in front there and then just distribute that as I do that mathematically. So 5i minus I would be 4i, and 5j minus 6j is minus j. So this right here represents delta R. And if you look at my diagram over here, you can think of the displacement vector as having two components, 4i and minus j. So we can easily get to that mathematically, and that's oftentimes the way that we will sort of rely on our techniques to be able to get to that final answer. But graphically, it certainly helps to understand that here. Let's take a look at what happens regarding average velocity. If this object is moving along a convoluted path like this picture shows here, if I wanted to determine the instantaneous velocity, I'm just going to let the time interval that I'm considering here change. So instead of me considering P1 to P2, I'm just going to shrink that time interval and consider what happens to the instantaneous velocity as I let delta t approach 0. So as I take the limit as delta t approaches 0, of delta r to delta t, I get dr dt, and that represents the instantaneous velocity of that motion. And you can see, actually, if I look at this diagram here, it actually is becoming a tangent to that actual curved path, very much like when we saw when we took a position time graph and took the derivative of that position with respect to time. I saw that the slope that we got was a slope of a line tangent to the curve. It's very much like what we have here, except this is dealing with motion in 2D. So again, very similar technique. Let's take a look at what that might mean when we look at acceleration. Now we consider the same kind of object here, moving from point 1 to point 2 so along some convoluted path, and I have some instantaneous velocities at those two particular spots. If I wanted to determine the instantaneous acceleration, I would again allow the time interval to shrink and take the limit as delta t approaches 0 of that ratio of delta v to delta t, and I get dv dt, the instantaneous rate of acceleration for that object. Again, if I were to shrink that up into a smaller time interval, I could sort of consider what's happening to the acceleration of the object as it starts to move through this path. Let me show you what that would look like graphically as I try to subtract v1 from v2. Okay? Again, acceleration is a vector quantity that is equal to the change in velocity divided by the time. Now, both of these things are vector quantities, right? Acceleration and change in velocity are vector quantities. And so they have the same direction. Let's consider that direction over here, doing that graphically. So here's v2. And I'm going to add to that the negative of v1. So if v1 is pointed up into the to the right there, the negative v1 would be pointed this way. And when I add these things together, again, tail to tip, what I get is a delta v that's sort of pointed inward, sort of toward the center of this circle. So I can sort of think of this as being the direction of delta v, and that's actually the direction of the acceleration as well. And when we start moving into forces, and we start understand how forces cause changes in motion, we can see that that force is actually in the direction of the object's change in velocity. It becomes pretty intuitive when we start looking at that graphically. Mathematically, we can get to those answers fairly quickly, but it doesn't provide quite the insight that graphical drawings do. Now, before I finish up this video, I just want to talk a little bit about how we might use unit vectors to describe both instantaneous velocity and instantaneous acceleration. It looks pretty complicated, but realize that any object moving in whatever kind of path that we'd like can be thought of as having some instantaneous rates of change in position that are pointed along the I hat, j hat, or k hat directions independently. So we can take this velocity that we're considering, instead of looking at the change in position, where r would again be sort of my my change in position relative to my origin, I can think of that as the time rate of change in my x position, plus the time rate of change in my y position, plus the time rate of change in my z position. Okay, so we can do that, and we'll show you a few examples in another video on how we might actually do that. Acceleration, same idea, can be written in unit vector notation. Take a look at this table 3-1, kinematic equations for constant acceleration in 2D. You should recognize these equations. These are exactly the same equations that we use for 1D, but you notice now I have subscripts for x direction and subscripts for y direction. If I wanted to deal with 3 dimensions, I would just have another subscript for z direction. And again, it's really that straightforward. We just use these equations to describe motion in the x. We use these equations to describe motion in the y. Sometimes an object might be moving with no acceleration in the x, but some acceleration in the y. We can use these equations to describe those. Ultimately, when we study projectile motion, we'll see how we might combine motion that's horizontal with motion that's vertical, and doing that just simply by considering the independence of that motion. That'll certainly come in our next section. And that completes the video for vector kinematics. I'm going to put another one out there that shows you some examples on how we might apply these ideas to some actual problems that you'd see in your homework.